Today we review all our functions, all the domains and ranges, and it's so nice to have this walk down memory lane here. Our linear function, which of course is all real numbers, all real numbers. We review our shifting patterns, left 2, down 1 for the absolute value function. So domain is all real numbers, range greater than or equal to -1. Negative x squared plus 2 we recognize as a parabola that's moved up 2, all real numbers for the domain, and the y values are less than or equal to 2. Plus or minus the square root of x minus 4 plus 2, so it's 1, 2, 3, 4 right and 2 up, and then the plus or minus makes it go that way. So now the range is all real numbers, but the x values are greater than or equal to 4. Here with y equals 1 over x, now we've got that rational function where the x's are not allowed to be 0, the y's are not allowed to be 0. For the exponential graph, that's moved, right 3, like that. So we still have the domain of all real numbers, range is greater than 0, and then log base 3, that's just a little bit steeper where its x is positive and the range is all real numbers. You want to make sure here that you get that the domain is in between -3 and 3, and the range looks like it's in between -1 and 1. We want to be able, especially next year in pre-calc, to look at just an equation and know the domain and range. So we know that all lines are all real numbers, versus this is just that horizontal line, so the range is 5, the domain is all real numbers. Here this is going to go, left 1, down 3, so the range is greater than or equal to -3. Negative x squared, of course the domain is all real numbers, but the range is less than or equal to 0. Here with the rational, we see that the x is not allowed to be 3, and then the y is not allowed to be 0. Next one is rational, so we're looking at the denominator to say that x is not allowed to be -4 or 4. And then the range is not going to be allowed to be 0, of course, because the numerator is 2, and you can only have 0 in a fraction when the numerator is 0. Here I just noticed that it's understood to be positive, so I might want to even picture the graph here and be like, oh, right, the x's are greater than or equal to 2, the y's are greater than or equal to 0. So it's not a problem to picture the graph. Here the y is greater than 1, and then it's all real numbers. But you want to be able to picture that in your head. Now when we're evaluating functions, you're just plugging in that value for x, or 2 minus 1, or 1. When you're plugging in the value x plus 3 quantity squared, right, you want to square that first, remembering that that's a FOIL question. Then distribute the 2, and then 18 minus 1 is 17. F of x plus 3 is different. Now you're adding, 2x squared minus 1 plus 3, or 2x squared plus 2. 3 times f of x is 3 times the quantity 2x squared minus 1, or 6x squared minus 3, and then f of 3x, 2 times 3x quantity squared minus 1. So each one here was just like a slightly different problem, right? Great, so if we want to find g of 1, we're looking for what's the y value when the x value is 1, which is of course 1 because it's a closed circle. G of 0 is 0. G of 3 is up here at 1, 2, 3, 4, 5, 6, 7. Looks like 7. The domain of G, it goes between 3 and then it goes everywhere in that other direction. So I would say less than or equal to 3 and greater than or equal to 0, of course, because of that up arrow. Here you're looking at which rule am I using? H of 7, since 7 is bigger than 0, is 2 times 7, or 14. But -3 is less than or equal to 0, so I'm going to plug it into that rule, which gives me -8. 7.5 is bigger than or equal to 0, that doubles to 15. -2, -6 plus 1 is -5. Great. Now we're graphing this piecewise function. So here, let's see, and I just have the final thing. So 3x plus 4, 1, 2, 3, 4, and then it's up 3 over 1 or down 3, back 1. But I'm only taking it, so I'm kind of drawing the whole line here, but I'm only taking it at an open circle here. So I'm going to draw that here, open circle this way. And then x minus 3 if x is bigger than 1. So that's a -3, and then up 1 over 1, or down 1, back 1. X is bigger than or equal to -1 will be the closed circle there. Negative x squared is, of course, an upside down parabola, but I'm only taking the piece when the x values are less than 2. Excuse me. So that would be 2, negative 4, and then this piece. So I can basically kind of erase that piece. There we go. And then y equals x if it's greater than or equal to 2, so that's from the point 2, 2. Although I messed up my open circle, closed circle, didn't I? That one here should be a closed or open circle. 1, 2, 3, 4. There we go. Perfect. So if we're going to go left 2, this is going to be x plus 2 squared versus right 2 is x minus 2 squared versus up 2 is x squared plus 2, down squared x squared minus 2. Reflect over the x is negative x squared. Reflect over the y is negative x squared. So then if I want to have that parent function up 2 and reflected over the x, it would be negative x squared plus 2. Here, this cube root function, down 6, left 2 reflected over the y. So it would be cube root of negative x, left 2 plus 2, and then down 6. And then here, if I want to go up 4 and right 2 is x minus 2, and then up 4. Perfect. For inverses, they just switch the x and y, so it's going to be 1, 2, 3, negative 1, 2, 5. And that mapping it didn't copy, so it would just be reversing it, right? Switching the x and the y. So same thing here. I guess I didn't do it, but you would just list the ordered pairs and flip them. And we know that the relationship between the graph and the inverse is a reflection over y equals x. So here, if I graph the line y equals x minus 4, up 1 over 1, up 1 over 1 here, the domain and range are all real numbers. If I switch colors here, if I want to find the inverse, it's x equals y minus 4. So when I add 4 to both sides, it's x plus 4. So 1, 2, 3, 4, and then up 1 over 1. Yep, all reals, all reals. Here, x squared plus 2 is my parabola that's moved up 2, so it's all reals, greater than or equal to 2. If I switch the x and y, and I'm fine to just do it like that, and so I'm going to get x minus 2 equals y squared. When I square root that, it's plus or minus square root of x minus 2. So that goes right 2. So the x values are bigger than or equal to 2, y values are all real numbers. Here's an exponential, so this is going to go through 1, 3. So here is all real numbers, y is greater than 0. If I switch it, instead of y equals 3 to the x, it's going to be x equals 3 to the y, which if I rewrite that is the log base 3 of x. I just like to reverse the order pairs. Instead of 0, 1, it's 1, 0. Instead of 1, 3, it's 3, 1. And then I can hug the axis there. X is greater than or equal to, greater than 0, all real numbers. Plus or minus square root of x minus 2. Now I'm going to go right 2. So this is domain of greater than or equal to 2 and all real numbers. If I switch that one, x is plus or minus square root of y minus 2. So if I square both sides, equals y minus 2. So this is x squared plus 2. So it's basically the reverse kind of the other one that you did. Domain is all real numbers. Range is greater than or equal to 2. The rationals can be kind of tricky. The original one here has that dotted plus sign, so the x is not allowed to be 0, the y is not allowed to be 0, and we have that rational graph. Now here's the interesting thing. Y equals 1 over x. When I switch it, x equals 1 over y. When I solve this for y, I'm going to get y equals 1 over x again. So not every rational is its own inverse, but if it's just 1 over x, it's actually its own inverse. The natural log function, 2.718, you can just do like that kind of swoop and say x is positive in all real numbers. And then you might even know by heart that it's e to the x here that flips up like this with all real numbers and greater than 0. Perfect. The last one's here, evaluating f of 2. It's just saying what is the y value when x is 2, or what is the y value when x is 7. For the h function, I'm actually plugging that in. 15 plus 4, the absolute value is 19. 18 plus 4 is 22. For For the g function, that's just in this table, so I'm just reading the values off the table, and then f of negative 5 is 9. For composition of functions, g of f of 5, you're going to plug that in. 5 squared is 25. 5 times 25, 125. F of g of 5, so now it's f of 25, which is 25 squared, which is 625. So those are different questions. G of f of 2 is 4, g of 4 is 20. And you don't even have to show any work for these. G of 2 is 10, f of 10 is 10 squared, or 100. Same thing here. I mean, it's probably overkill. G of f of 2 would be g of 4, which is 12. F of h of 2 is f of 1, which is 1. F of g of h of 2 would be f of g of 1. G of 1, of course, is 3, and 3 squared is 9. If you have it with an x, though, f of g of x minus 1, 3 times x minus 1 is 3x minus 3, and then you could probably leave that as 3x minus 3 quantity squared, or you could FOIL it out. F of g of 4, let's see, well, g of 4 is 2, so this is f of 2, which is 7. G of 5, so that's g of 4. G of 4 is 2, and g of 2 is 5. G of 7, I'm going to do this in my head. G of 7 is 7. F of 7 is 4, and g of 4 is 2. These questions, when they ask for the inverse, is saying what is the x value when the y value is 2? What is the x value when the y value is 2? G of f of 0, let's see, f looks like the pink one, so f of 0 looks like 3, and g of 3 looks like 1, 2, 3, 4. F of g of 3, well, we just said g of 3 was 4, so f of 4 looks like negative 1. F of negative 4, f is the pink, so that looks like negative 2. If I put in negative 2 to the g, that's going to be 1. And then g of 1 looks like 1. To show that those are inverses of each other, you would do something like f of g of 0, and then show that it gets back to 0. So g of 0 is 3, and if I plug in a 3, I get back to 0. So, and you could choose any number. I just chose 0 because it was the easiest. There you have it.